Hi, we are Group B ITC and we will be presenting the Buffett and 8051 microcontroller project. So here is the Buffett game on the left and the 8051 chip on the right. Group B ITC consists of Paul Jordan, who is the group leader, Alan Kelly, myself, Zainab Alawali, and Richard Finn. The content of the presentation consists of the introduction, what a microprocessor is, how a microprocessor works, example of code, tool flow, design issues, how to improve design, and finally the conclusion. So, what a microprocessor is. A microprocessor is an integrated circuit on a tiny silicon chip that contains thousands or millions of tiny on-off switches known as transistors. The transistors are laid out along microscopic lines, which are made up of superfine traces of aluminium that store data. These circuits store data in certain patterns that can be programmed by software. One of the biggest tasks microprocessors perform is acting as the brains inside a personal computer. Computers are not the only way in which microprocessors are used. They can be used to help many devices, for example, your car, traffic lights, telephone, to remember and adjust to incoming information. One way in which it can be used on a telephone is by letting it redial. How a microprocessor works. As we know, the microprocessor is the central processing unit in a computer. It receives, transmits every command and process carried out by the system. Electrical currents moving through wires and transistors are converted into usable messages through the use of Boolean logic language. Based on the on-off switches of the current moving through transistor circuits, this Boolean logic communicates system commands to and from receiving devices within the computer. The microprocessor communicates within the primary capacities. These are logic and processing of information. These processes are handled by two components within the chip, which are arithmetic logic unit, also known as the ALU. This is responsible for all commands requiring arithmetic for logical function, and control unit, also known as CU, which handles the information processing from the computer's memory. I will now hand you over to Paul, the group leader, who is going to be doing an example of code.
Now, this is just an example of some of the code. The subroutines which are at the very end are still the same as the ones that were used in the previous screencast, so we'll just run through the start of it. The line 5 to line 16 here is for the interrupt. Now the accumulator and the PSW need to be pushed onto the stack to protect them while the interrupt is running, but they also need to be popped back off the stack at the end to get them back. And on your return, there's an I has to be added to the end to show that you're returning from the interrupt. On the main program, the switches are just identified here, just to make a few constants so that changes that are needed can be made easily throughout the program. Then these lines of code here this is just for where the high score is going to be stored. This is where the timer length is going to be stored, and this can be changed by selecting the easy or hard functions, and this is where the current score is going to be stored. When you're starting up, then your high score obviously has to be set to 0. Then your resetter jump is going to come in after your high score, otherwise your high score is going to be reset every time you hit the reset button. So at this point here now, you're just enabled both the interrupts and setting your current score to 0. And as a setup on this, your timer length is set to normal, which is moving 31 into your timer level, and then that jumps down to the set level subroutine and initialize your LCD. So this just your subroutine to start up your LCD display and get everything up and running. This line here then sets up your randomizer. Once the randomizer is set up, then you can jump down into playing the game, where you will see that it will stay until each of the switches is hit, and then if you're not hitting within the time, then it just jumps down to end game, and that's it, gone.
Okay, so we've seen how a microcontroller works and an example of our code. So this is the final project that we've designed anyway. So I've seen another screencast. A lot of it is very much the same. We have our LCD and our microcontroller, but we've now added 4 switches. a reset button and a level select. So by default it is normal, and you can select easy or hard. So we'll start with a demonstration of this working. So LC loads into switch 1, switch 4, 3, and I've hit the wrong switch. It stops. So I scored 3 and the new high score is now 3, originally set to 0. So if I click on reset, it'll start again. So I got it wrong again, scored 4, so the new high score is 4. So if I reset it and just let it time out, you see at about 2 seconds it should just time out. As time out, I scored 0, so the high score is still 4, and it continues on working as intended. So that's our simple setup of the Bop It game. So let's talk about the code anyway. So we've already seen an example of a code, so here we'll talk about a few bugs that we encountered. So one such bug was, because our switches are on port 3, switch 1 is 0 and switch 4, when we take the whole byte, actually comes in as 8. So we need to basically put in a little software decoder to break it down to switch 1 is 1, switch 2 is 2, and so on. So this is our simple little bit of code. So when our program tries to check which switch is pressed, it converts the switch to its relevant number. So switch 4 will be 4, and when I check it against number 4, it should be okay. If it's the wrong switch, the game will end. Another bug that was worth mentioning was calling subroutines. So our code here has a lot of subroutines, like I called, but for instance, if I call command right here, this subroutine, and I have set R6 maybe to a certain value, I don't want command right to change that value if I need to use it here. So one routine to get past this would be to push your registers onto the stack and pop them back off if you're afraid that they'll be used. So luckily enough, we don't use a lot of them, or they don't need to hold their values, so it wasn't much of a problem, but it's worth noting. One very big migraine that posed a problem was our interrupt timer. We had a problem that when we ran ISIS and we reset ISIS, the counter stopped working, so it would never time out after the first game. So the problem turned out that I had this little line in here that jumped out of our interrupt. So the return for the interrupt never got ran, so the interrupt never worked properly after the first time. So this was a huge headache. Taught different problems, stack overflows and securing the accumulator were all a problem, none of them, but it just took a while to debug, so it's another one worth mentioning. So improvements to our final design. As said, we use a software decoder for our switches. I think a big improvement here would be to use a hardware decoder, which would mean that we could have up to 255 switches, and we wouldn't really need to change any code. You just keep adding the switches and then check that the right switch was pressed. I think that would be a big improvement. Another thing I don't know if we're seeing, if I run again and I play the game here and I get a score of 1, we'll say, the high score is 1. If I then run on easy mode and play the game, the high score is still 1, and then if I play it and get a better high score, the high score is now 2. Improvement here would be to have a high score for each level. It would be ideal, but we didn't feel it was key to stick in at the moment. That's it for our improvements. So okay, so to conclude, we've seen how we've designed, built, tested, debugged and finalised a Bop It design in ISIS using an 8051 microcontroller. So throughout this program, or throughout this project, we have learned how microcontrollers work. We've learned how to set up an environment to simulate a microcontroller, how to write code for it, how to launch the code on a microcontroller, run it, and to simulate it. We've also seen how a microcontroller can interface with other devices, and how we've managed to build and simulate that as well. We've also developed a lot of skills throughout this project, including communication skills and teamworking skills. Throughout the design of the Bop It, we had to work in a team in a non-face-to-face environment. So we had to learn various tools, online tools mainly, that include Skype, Twitter, emails, and anything else that allowed us to communicate efficiently without actually talking face-to-face. So that is our project. It's our Boppa design working, and thank you for watching the screencast.